All right, well, let me get going. I'm sorry I don't speak Hebrew, so you're going to have to suffer through my Bostonian English, so I'll try to speak somewhat slow, but I can't guarantee it'll be too slow. So hopefully you'll be able to understand me reasonably well. So what I'm going to talk about today is really around net zero laboratories and sort of how to get there, some examples of net zero labs. And then I also want to talk about the group that I now am president of. It's called the International Institute for Sustainable Labs. Eric sort of referred to it. We usually just call it I2SL for short, sort of keep it a little bit brief. But again, I want to talk a little bit about that as well and some of the programs we're starting on, and we're hoping to see if we can start a chapter here in Israel, so we'll talk a little bit more about that as well. So the key here, I think that sort of draws us all together is this concern around obviously climate change and global warming. And if you look at sort of the numbers, it's really startling that we don't have a lot of time to move quickly to protect the environment, protect the world, and protect our species from extinction. If you look sort of at the numbers, you can see that if we want to try to keep it to the 1.5 degrees, which has been shown as really a critical point that we want to protect against, or even 2 degrees, which even that half degree, which doesn't sound like much, can actually make a huge difference in a lot of the environmental effects. But even a 1.5 to 2 degree change require us to make significant cuts in our carbon emissions. And to try to keep to the 1.5 degrees means almost a 50% cut by 2030. So we have a lot of work to do. We need to move quickly to make change. And that one of the issues we have to do is try to make our buildings, even all new buildings, sort of net zero in terms of their carbon emissions. And then over the next 5 or 10, 15 years, try to move the building stock into this sort of net zero carbon emission standpoint, which sounds daunting, but the technologies are out there. It's not impossible. It can be done. There's proven techniques for doing it. It's just a matter of executing it and having the will to go forward and do this. So first thing I wanted to talk a little bit about is what does net zero mean? Because there are many definitions for net zero. There's net zero energy, you'll hear. There's net zero carbon. What does all that mean? So really what a net zero energy lab may not necessarily be a net zero carbon, which you might find strange, but the point here is that if you have, let's say, a building that has a photovoltaic array and it's basically actually providing power back to the grid during the day, and then maybe at nighttime it's pulling power from the grid, even though that may end up being zero energy pulled from the grid, that's still not a net zero carbon lab, because that energy that's pulling from the grid, if the grid is not zero emissions, if the grid is still dirty, has carbon emissions, then that building is still consuming carbon. Even though it's providing power during the day, it's still sort of net carbon emissions. So we have to be a little bit careful about that and find ways to truly make the building net zero on a carbon basis. You also hear the term sometimes net zero carbon ready. And this issue is really trying to move these buildings to basically eliminate fossil fuels on site. So less of an issue here in Israel since you don't have a lot of heating, but in the US where we have a lot of heating, natural gas is a common fuel used for heating the building. And so now we're beginning to eliminate the use of natural gas, moving to heat pumps, moving to heat recovery chillers and other means to basically electrify, sort of the term, electrify the building. So we're not using any fossil fuels. In fact, in New York City, as an example, they passed, it's called Local Law 97, but that law basically prohibits any use of natural gas in new buildings. So literally, if you're building a new building in New York City, you cannot use natural gas. It has to be 100% electric. Now, they do have exceptions for hospitals. They do have an exception for laboratories today, but that's probably going to go away soon as well. So we're seeing this massive shift away from using fossil fuels and obviously making the building at least to the point that it's using all electricity. And then the hope is that when the grid becomes clean, which hopefully will happen soon or at some point, then obviously the building will be a net zero building because it's using clean electricity. The other issue you hear is net zero on-site versus net zero off-site. The difference there is really where is that power coming from. Obviously, we're going to reduce the energy use of the building, but then we have to use some power. And if you're using on-site like photovoltaics, that would be an on-site facility. But also a lot of things that people are doing because they don't have the space or the money to put in a big photovoltaic array on their facility, what they're doing instead is using these power purchase agreements where they're basically buying solar photovoltaics someplace else and then basically buying that power in an agreement. Now there's sort of different thoughts about this, but to be most environmentally conscious, really that money should be going to purchase new solar photovoltaics. If you're just buying existing hydroelectric power, that's not really doesn't really count. So the idea is that if you're buying new photovoltaics, whether it's on-site or off-site, that's fine. And then obviously they have these agreements, so rather than spending the money up front, you create an agreement that you're just buying power for 20 years from this facility that's being built by some other organization, and then basically that power is effectively being used by yourself. So on-site, off-site, again, it doesn't matter. It's really the key is, are you sort of net zero in terms of this emissions standpoint. So really there's three sort of things we need to do here to make the building net zero energy or net zero carbon. And basically it starts with trying to reduce energy as much as possible. So we want to reduce that as much as we can because that's going to cut our costs. It's going to cut the amount of energy we use. At that point, whatever energy we are still using, we want to use energy recovery means, reuse that energy. If there's waste heat or things of that nature, we want to try to use that. So it's sort of a heat recovery or other types of recovery systems. And lastly, whatever's left over, obviously that's where we use our renewables, off-site or on-site. So again, very doable, very possible. It's becoming it's becoming more common now. So this trend started many years ago. The first net zero laboratory building that I'm aware of at least was built back in 2013, almost 10 years ago. It was called the J. Craig Venter Laboratory. So the guy, Venter was one of the early gene sequencing machines. They were the first ones to sequence the genome. So this is it was a laboratory. It was these architects were ZGF and Integral Group engineers out of the U.S. Again, about 4,000 gross square meters, about some below-grade parking as well. So this facility was a net zero facility. They used a lot of different techniques to do that, trying to use natural ventilation in this area, sort of a courtyard area as an example, rather than having it enclosed, they made it open. This laboratory is in Southern California, so it's a very mild climate, milder than here in Israel. So they were able to do things like that. They also, it's sort of a small laboratory, about 750 square meters or so of wet lab space. Again, a reasonably, not too large, but a reasonable size photovoltaic array that was used for the building. You can see that this is where they reduced their energy consumption considerably, so they would have used, in a normal building, normal design would have been this much energy, and instead this is how much they use. So they effectively cut their energy use by about 3/4. And this is what you're going to see this as I go through these different buildings. You're going to see this over and over again, that there's typically about a 70 to 75% reduction in energy use in these sort of net zero facilities. So that when you get that low, then you can, a lot of things happen. You can begin to cut your first costs because you have less equipment. And again, the power photovoltaic requirements, PV requirements, they become manageable for the facility. But they use some different technologies to do this. One was a thermal storage system. Again, these are conventional approaches. There's nothing crazy here. These are standard approaches that people use. So they use a thermal storage system. Another common theme you're going to see over and over again is the use of chill beams or some sort of local cooling system for the laboratory, so you avoid the use of reheat. Demand-based control, which is sort of the Aircuity system, is a common theme to get the air changes down. So a critical aspect of these facilities is they tend to work with less air change requirements. So be a demand-based control system, or maybe they've done some control banding or other means to try to reduce the air change requirements. This approach, they're using 4 air changes during the day, 2 air changes at night. But if they sense chemicals in the lab, then obviously they increase it to a higher purge level, typically around 8 to 12 air changes from a purge standpoint to clear the air if they sense some contaminants in the environment. So that was a J. Craig Venter lab. That was, again, almost 10 years ago. In 2016, so now we're moving forward about 6 years ago, in my mind, this is the one was sort of the second laboratory, sort of net zero facility. Another group of engineers and architects, Sasaki and BR Plus A, the large firms in the U.S. Again, about 5,000 gross square meters. Again, similar, they also had a sort of atrium area, sort of a naturally ventilated area. Now this building is in Massachusetts, sort of my home area, so the climate is much colder, so it's a more harsher climate, but again, still able to meet the net zero requirements. And again, more lab space than the Craig Banner Institute, sort of a larger facility. Again, the whole key is they reduced their energy considerably. You can see about a 45,000 BTU per square foot sort of level of intensity. And again, they had on-site solar. Basically, what they did there is they have a large facility, about 2.3 megawatts. For the lab, they didn't need that much. You can sort of see this is the lab area here. This is the photovoltaic array. It's basically one of these parking lot type things where they basically put the photovoltaics over the parking lots. They shade the cars, so it gives a dual benefit. But the key was that they used around 450,000, 450 kilowatt hours of capacity. Well, actually using 750, sorry. But about 22% of the array. So the array was there, it was a power purchase agreement situation. They didn't buy it, didn't have to pay up front for that. They basically leased it effectively. So the way to think of these agreements are like lease agreements, so they're paying over time, so it made it more attractive to them. And again, that photovoltaic array is powering a lot of the site, not just the laboratory. What you see here is also some of the technologies that they used in this building. So in this case, they using ground source heat pumps. And this area here is seen as sort of more of a conventional design. This is obviously the design they use, which is the net zero design, so a little bit more aggressive in what they're doing. So using ground source heat pumps. They're using fan coils, so they didn't use chill beams, but they're using fan coils, but same concept of local cooling. So they're bringing air from outside, but that air is only for makeup. It's not for cooling, and the cooling is done with, in this case, a fan, just a regular fan coil. So versus using a chill beam, they're using fan coils. But the same concept. This is the way they can reduce the airflow requirements. So they're just bringing that air in for makeup. And then they've been able to reduce the air change requirements by using a demand-based control system again, like we talked about before, sort of air quality monitoring, sort of an Aircuity type system. They also use some filtered fume hoods. So these are fume hoods that don't exhaust out of the building. They're basically going back into the room and they're filtering the contaminants. You have to be careful about using these devices. Fortunately for this type of building, it wasn't just research. There was some research, but a lot of the fume hoods were for teaching areas where they knew the contaminants, knew the chemicals they were working with, so they were able to know that the filters they had in these chemical sort of filtered fume hoods would obviously filter out the contaminants. So they were able to safely use those fume hoods for this application. So you can't always use them. I mean, it depends on what type of research or if it's more of a teaching environment where you know the chemicals you're working with. They also used an enthalpy wheel, so that's used on the general exhaust. You're not going to go take that contaminants from a fume hood and put it through a enthalpy wheel. You're only going to use the enthalpy wheel for general exhaust, so the cleaner air from the room. But that, again, can be helpful. You can sort of see that here. And then, again, as I said, in the non-lab areas, they're able to use some natural ventilation. Not all the time, because it obviously gets very cold in Massachusetts during the winter, but certain periods of the time they can open up these louvers and basically provide a naturally ventilated environment. And outside the lab, this is more in the office areas. So those are some of the techniques they used to make this building, to reduce that energy. And again, bringing the energy down reduction of about 70%. They actually used less energy than they had predicted, so they did very good in terms of their models. This is just showing what they predicted for energy use, basically from the different sources of energy consumption. They actually did much better. In fact, they would have done a lot better, but they had an issue with their domestic hot water system. That's this big blue area. They thought they were going to use a dual gas system, but it didn't end up working out as well as they had predicted, so that used more energy. But even with that, they still were under their projections. Nowadays, they wouldn't use natural gas anymore. I mean, this is really the change in thinking now. You see in the last few years where people have gone away from natural gas completely. So again, it's the idea that we're going to electrify. So instead of this, they probably would have used heat pumps or other means to provide that heating. So, but again, this is built almost 6 years ago. So bottom line is that with all that technology we added into the building, or was added to the building, the increased cost was less than 1%. And actually, because they were able to get some incentives from the local utility, they actually saved money over the original design of about $200,000 less expense than they had originally predicted based on a standard design. So it actually, effectively, not only did they save all this energy, but they also saved first cost. And again, the whole idea is that by reducing the energy requirements, reducing the airflow requirements, they could use a smaller HVAC system. So obviously they had to pay for some extra controls, but that extra controls cost was basically covered by the reduction in the HVAC system. So net was basically neutral or even a slight, very slight change in cost. And again, as I said, total energy use was significantly reduced by about 70%. Going to a more current design, this is a project that was just recently completed about a year ago. It's the California Air Resources Board, which is sort of called CARB. That's their headquarters and laboratory. This is now back in Los Angeles in California. This facility, it's not the facility, but the organization is sort of famous because they're the ones that came out and discovered that the VW had the trick program, which is trying to basically falsify or trick the emissions programs to, so they actually were exhausting a lot more emissions than they claimed, but they had a little program that when they were testing it, it would basically, fool the program. But the CARB group was able to figure that out and discover that these cars were not meeting what they said. So again, they do a lot of testing at this facility in addition to doing research. So it's a larger facility, about 37,000 square meters. And again, they have about a 3.7 megawatt facility in terms of foldable tags, which you can see there sort of on top of the buildings, on top of the parking lots. So this you can sort of see the facility, how it's laid out. So here's the laboratory here, about 3.3 3,300 square meters roughly. They have some office area. They have some. This is more like car testing. They do some truck testing. They have some test vehicle parking and staff and other areas. So very interesting project. So this is their slide. This again is from ZGF. Another again they're the same ones that did the Craig Venner Lab and AEI, which is another firm, engineering firm in the U.S. But again, this is their slide showing again the same thing I was sort of saying. You basically first want to do everything possible to reduce the requirements. So when you do your planning, what can we do to use less energy just from a planning standpoint, from a design standpoint, not getting into the equipment, but sort of how can I reduce my requirements? Do I really need to have that fume hood? Do I really need to put in this equipment? What can I do to reduce those requirements for energy? Once we've done that, then obviously we get into what I talk about, which is obviously getting the right equipment to reduce the energy use, use heat recovery, those techniques. Then obviously we add the renewables, and lastly, hopefully we have a surplus of energy, which this building had. So again, from a chemistry lab standpoint, what were they doing? Again, some of the same things we talked about, a demand-based system we talked about earlier. They're using some dual lighting and HVAC occupancy controls, using some sensors on the sashes to reduce the sashes and lower the velocities of the fume hoods, using chill beams again, like we talked about. So again, you see that as a common theme to be able to decouple the cooling from the airflow. So we reduce the airflow down, have the airflow be internally cooled in the lab, so we're not bringing air from outside, this massive amount of airflow from outside to cool it or heat it and bring it into the lab. Just use a smaller amount of airflow in the lab and then cool with devices in the lab, chill beams, fan coils, those devices. So from other techniques they did, they used a dual temperature chilled water system. So basically 2 temperatures, 14 degrees C and a 5 degree system. That idea being that a lot of the time they didn't need to dehumidify based on the climate, so they're using sort of a higher temperature water, chilled water, since that, when they can. Sometimes they would have to use the lower temperature, but for the chill beams typically use a higher temperature water, so they can chill water. So for that reason, they can use that higher temperature. But occasionally they do need to use the lower temperature, so it's a dual temperature system. So, but overall, quite efficient. And again, using heat recovery chillers, another technique as well for saving energy and getting rid of the natural gas. Last project mentioned is actually from here in the Middle East. This is in Abu Dhabi. It's a project we worked on actually almost again about 10 years ago. This didn't hit net zero, so it's not technically a net zero lab, but it was a near net zero. They didn't quite make it. The requirements ended up being more than their on-site photovoltaic needs. They had a 10 megawatt array, so it's a pretty large array, but very large facility, about 25,000 square meters. Of labs, and then the whole facility is about 150,000 square meters. So it's a big facility. It has residential, has it's really a campus-type facility. So they've got classrooms and laboratories and other types of facilities. So again, I mean, same sort of technologies. They obviously have variable line lab controls. Then the demand-based controls, lower fume minimums on the hoods based on new requirements that have come out around that time. These are some of the laboratory ventilation requirements. Again, using low pressure drop design, sort of varying exhaust fan velocities with some techniques. Chill beams again, common theme, and lastly heat recovery. So these are the classic approaches that people are using. And again, this is, they were using a combination. In some labs they had chill beams, in other labs they had fan coil units. So again, same idea of using this. They were actually using 2 air changes. The chill beams typically need more than, oops, I'm sorry. Typically, sorry. So the chill beams typically in this environment would actually need about 4 air changes to operate, just in terms of the way they work. They didn't want to use that much airflow, so they're actually using a sort of a fan-powered box. So they're actually bringing 2 air changes of outside air, and then they're using 2 air changes of air in the lab, and that's then going through the chill beams. So the beams are actually getting 4 air changes worth of airflow, but again, only 2 of that is coming from outside. So again, just using that air from inside. Sort of almost like a cross between a fan coil unit and a chill beams, using sort of both. And then other labs, which are smaller, they just used fan coil units. But again, that's sort of common theme of very low airflow from outside, cooling with these chill beams or other local cooling units, and then having a purge capability when they sense chemicals or contaminants, they can go to a higher airflow. So it's sort of a theme that these labs at least were using. So again, you hear this number over and over again, but their reduction was around 74% from more of a standard design that they would have used. And you can see how that broke down. This would have been more of a standard design running with 6 air changes with more conventional technology. Using the demand-based control running at 2 air changes day and night, with obviously the ability to purge up to about 14 air changes when needed. That reduced the airflow and reduced the energy by about 53%. They added in the chill beams, sort of good low pressure drop design, some variable exhaust fan controls. That brought it down to 68% reduction. And then lastly, they added an FP wheel, which brought them all the way to 74%. So in that sort of range, again, of what they're trying to get to. Now, with all that being said, again, what was the first cost implications? Because a lot of times people say, oh, if you get that much energy savings, you must have spent a lot of money. Well, they didn't. Actually, it saved them money. So again, this was the base design, but because they reduced the requirements, because they didn't need as much airflow based on the use of this demand controls and other technologies, you can see that it reduced the requirements quite low. Even though they're adding in chill beams, the cost of the chill beams is still quite a reduction. I'll add in the demand-based control. That's a controls cost, which I didn't add in here, but I'll add it at the end. They then added in this is the cost of the heat recovery, so that's sort of paid for itself because the other equipment like the cooling system, the chillers and stuff were reduced because they didn't need as much capacity now. So that paid for itself. So again, not much of a change in cost because there's added cost here, but it's countered by the reduction in the HVAC system. Now again, there is then the cost of the controls, the demand controls and other equipment. So that was about $500,000 So net, it was about still a savings of about $300,000. So here we are, we've reduced the energy by 74%. Oh, and oh, by the way, we saved $300,000 in first cost. Again, this was not for the whole project. This is looking at just a piece of it. I didn't, it's a very large project. So this is looking at like a 5,000 square meter piece of the project. You can sort of scope it up, scale up to the whole facility. But again, very large savings for this project when you add it all up. So again, one of the key takeaways from here is that typically in these systems, and you see it over and over again, that the first cost is paid for by a reduction. Even though we're adding some controls and other equipment, that cost is paid for by the reduced HVAC equipment. We're using less chillers, less heating equipment, less airflow, less fans, so that's paying for that. The other benefit of this is that it also reduces your photovoltaic requirements. Now this project, they were buying the photovoltaics up front, so they weren't doing any leasing, and they were buying it, so that was an enormous reduction in cost. So the reduction of energy came out to equivalent to a PV capacity savings of about 4 megawatts, or about $20 million in first cost savings. So very substantial. If they were off-site, again, if they were like a power purchase agreement, they wouldn't have seen that first cost savings, but again, they would have seen a reduction in their payments because obviously they don't need as much power. So one way or another, you're getting that benefit either upfront or you're getting it over time. So I think, I guess my point here, one of the things I wanted to mention is that sometimes when you look at these issues around climate change and trying to hit these numbers, it can seem very daunting, and it's like, how are we ever going to do this? You try to project it linearly, and it's just not going to happen. But I think, I do have hope here that in these issues around climate change and these changes we're making to how buildings are built, change can happen very non-linearly. It can happen with like a tipping point, and I'm hopeful that can happen here. And I've seen even over the last year, I've seen a lot of change happening, where a lot of recognition of these issues, focusing on decarbonization, how do we get these buildings better. So I'm hopeful that we can reach sort of a tipping point and things can accelerate and move very quickly. And even in our industry, which I tend to think of as a slow-moving industry, the whole building industry, if you look at what happened with the whole LEED movement, the whole US GBC, and now obviously around the world, that happened very quickly. I mean, it really was sort of an exponential change. If you look at how rapidly LEED was adopted, it really was almost an exponential change. Once it got hold, once it reached a certain level, it moved very quickly. And I'm hopeful that can happen when we look at how our buildings are built and designed and operated, that we can move to this more of a net zero concept or a very low carbon emissions approach. So again, when we look at net zero, just to summarize this part of my presentation, the key is that, low air change design is very important. Obviously, airflow, we've heard from others here, whether it was earlier presentations, that's an important aspect. We want to reduce the airflow as much as possible so to reach these low energy usage. Again, these issues are proven. We've done it. There's quite a few of these designs. I know at least in the U.S. we see a lot of projects that are now being built as electrified, net zero type facilities, or net zero ready, that maybe they're not building the photovoltaics, but once the grid becomes neutral, those buildings will be net zero carbon as well. And again, it doesn't need to cost more. So this is not a first cost issue. It's really just a question of deciding you're going to do it, using the right designs. It doesn't have to cost you more. So it's not a first cost problem. It's really just an issue of saying we're going to do it, using the right type of design, and it can be done, and it doesn't have to cost you more. It may even save you money. And as I said, even when you look at the photovoltaics, people say, I can't afford putting in a megawatt of capacity. Well, fine. Use a power purchase agreement. That way you're just buying your needs over time. It's basically like a lease, so you don't have to buy it up front. You can pay for it instead of paying the power company. You're paying this, basically the power purchase agreement company. Again, it's become very commonly used. So again, that's a very proven approach as well to basically buy that photovoltaic capacity without having to pay for it up front. Okay, so that's basically what I wanted to say about the Net Zero Labs. But you might say again, well, all this sounds good, Gordon, but how do I really do this? And what are the different, you mentioned some technologies, but how do I implement them? How do I use them? What are the other case studies? And that's where the organization that I'm now president of can help. This is the International Institute for Sustainable Labs. And our focus is around making labs more sustainable, decarbonizing laboratories around the world. And if you wonder how this started, basically this started as a program from the federal government in the US. It was called Labs 21, or Laboratories for the 21st Century. It was a program really started in 1997, came out of both the EPA, the Environmental Protection Agency, as well as the Department of Energy, the DOE. And again, the goal was to improve the energy performance of laboratories. And a lot of this revolved around an annual conference. The first one was in 1999, and then every year after that, we had a conference. In about 2005, the EPA and the DOE decided that they weren't really into the conference business, that they felt this was something that should be done by somebody else. And it turned out that the person who really was found had really started this program within the government at the EPA, a gentleman by the name of Phil Werdzik, decided that he would pick this up. So he basically left the government, started a nonprofit, which is I2SL, and then with the agreement of the government, he began to take over the responsibility for this program and for the conference, and fully took it over by sort of a transition over a few years, and by 2010, it was fully under I2SL. And really, I2SL was the first organization dedicated to lab sustainability. Today, currently, we have probably over 500 active members, in addition to a community of over 5,000, almost probably 7,000 people that we interact with on some basis. And we now have chapters, 12 regional chapters in the U.S., with actually 2 more forming. We have one starting in LA, literally about a month, and another one in Houston starting up shortly as well. And again, what do the chapters do is they take the knowledge. We have the annual conference, which is great. It's a good activity, but the key is to bring that local. So many people can't travel to the annual conferences, but when we can bring it to a local level, then more people can participate, more sharing of knowledge. And again, I2SL is unique. We're not like ASHRAE or architects like AIA, and that we really are focused around a market, around laboratories. So we have many different stakeholders, whether that's architects, engineers, lab planners. On the owner side, we have obviously facility people, but we also have the health and safety people. So we cover the wide gamut, manufacturers obviously as well, vendors. So we really bring together all the different stakeholders who touch laboratories to work together on how do we make these facilities sustainable. Because it does take many people. Many people are involved in these to make these decisions and make these things happen. So this is our goal, is to help bring people together, provide a means to network on a local level, which is what the chapters are very successful doing. So typically they have activities they might do, some are monthly, more likely they might be quarterly. So they might have a meeting sort of like this where you have a speaker and they talk, a chance to interact, maybe talk about different issues. Working groups, you might have a local working group working on something. That's sort of what these groups do. A lot of times they'll have like an all-day seminar, which many speakers that might form that as like a local conference basically as well. So again, sometimes they're just both events. So it depends on ways to get people together and talking. So it's been quite successful. We see a real need out there in the market for this. And we also have started these international chapters as well. So Singapore was the first one we started. We've had a very successful chapter in China, out of Beijing, and they've actually run their own annual conferences with literally over 1,000 people each, so very successful. India recently started, that's just sort of getting going, and Australia and New Zealand is in the process of forming a chapter too. So we've had these activities around the world. So again, and we also work with other organizations internationally too. So in Canada, rather than forming a chapter, the Canadian folks who were interested in sustainability decided to create their own organization, which is sort of an affiliate. We work together with them, but they are their own separate organization. Same in the UK. At one point we talked about having them be a chapter, but they decided it was easier for them just to operate independently on their own, which is fine. And we've worked together over the years. And then in Europe, we have a group called Agniton, which is based out of Germany, but covers all of Europe, has different members in the European community. And again, they were inspired, as these other organizations were, by I2SL. So we have a very close association with them. actually spent a couple hours on a conference on yesterday, talking with them on some issues related to ventilation. So again, if you think about I2SL, our focus is really above the ceiling. It's really on the building. We actually do work as well with the scientists. We do have some programs involving green chemistry or waste minimization, green research grants. So we do work in that area as well. But there's another organization in the U.S. that's more focused on sort of below the ceiling, which is the group called My Green Labs. So we work with them quite closely. We've had different programs we've worked with them on. One was a freezer challenge, trying to get people to use less freezers, consolidate their samples, throw the samples that have been sitting there for 20 years that you don't even know what they're for anymore, get rid of those and reduce and consolidate their freezers. So we work with them a little bit on that as well. But again, our primary focus is the building itself. It's trying to make the building more sustainable. But again, you can see it's really, that's sort of our theme, dedicated to both design, construction, and operation of these high-performance facilities. Energy efficiency is key, as well as the decarbonization of them. So where do we stand today? Again, why am I standing here in front of you versus talking about Aircuity or something? And it's really that we had a leadership change in the fall of this year. Basically, the president, Bill Wurzik, who I mentioned, had a heart attack suddenly and passed away very unexpectedly. I'd seen him literally 2 or 3 weeks before at our annual conference. Seemed in perfect health, and then literally passed away suddenly from a heart attack. Very, very tragic. I've been vice president for many years of the organization. There's an old expression about vice presidents you may be familiar with. The typical job of vice president. You wake up in the morning at 9 a.m., check, make sure the president's alive. If he is, you go back to bed for the rest of the day. That's the job of a vice president. So didn't have a lot of work to do. I've been always involved in the organization though. But when he passed away, everyone looked at me and like, what are you going to do? Well, okay. So I took on the role and I'm now president of the organization. So I've drastically reduced my Aircuity responsibilities. Technically, I still work for Aircuity, but more on a more advisory, part-time. I've dropped all my sales responsibilities and really focusing more on I2SL. We have an executive director as well, so I don't have to run the day-to-day, so that's at least good. But it's a full-time job. It's a lot of work, and it's a volunteer as well, so that's probably a challenge, but an important one. So one of the things that I've also been working on now and sort of pushing and sort of helping to promote is a new standard for decarbonization of labs. So, I'll talk about it in a minute, but it's around decarbonizing labs and how do we score labs around this. So again, we'll talk about that coming up. So the other thing I want to talk about is, you might say, well, okay, this is great, but what does I2SL really do? And a lot of what we do is knowledge transfer. So we do at this conference, again, I would invite you all to attend if you're interested in coming to the U.S. in the fall. It's a nice time to come to the U.S. in the New England or East Coast. So we have a conference that will be in Pittsburgh this year, October 16th through 19th. Again, the focus is around what we call climate solutions, focusing on decarbonization and sort of resilience. But again, there's other topics as well. We cover some of the green chemistry, waste minimization. We had over 120 abstracts submitted. We'll probably have about 100 presentations, so a lot of content, quite interesting. It's over a few days. But we also have a lot of written resources as well. We have what we call best practice guides, which give a lot of the how-to. So how do I decarbonize a lab? How do I reduce energy? How do I do this or that? So there's a lot of how-to guides. Some of that's been funded by the federal government, so helping us with that. We have a lot of sustainable case studies. Again, how do other people do it? An e-library of different articles. You saw the Smart Labs program that also Eric had talked about earlier at the video on. So we didn't develop the Smart Labs program. The Smart Labs actually came out of a program from the University of California at Irvine. They actually developed Smart Labs. But then the federal government was quite excited about it, saw all the benefits. Typically what Smart Labs do is that program will typically cut the energy consumption of a lab by about 50%. They have about 7 to 8 different steps of what you do, involving HVAC and lighting and all sorts of different things to reduce the energy consumption of a lab and do it in a safe manner as well. So that's been supported now by the Department of Energy, the NREL lab, which is the National Renewable Energy Lab. So we were funded by them to put this information on our website, so all it's free. You can download it. It's very good information about how to follow this program. And again, we have webinars, we have workshops, we're thinking of a virtual conference that would allow you to participate without having to come to the U.S. or other venues, so it's sort of an online Zoom type of situation. So again, these are the ways we've done to transfer the information. The other tool we have, which is very powerful, which we're now, as I said, going to work on, is a lab benchmarking tool. Now this tool, again, is very important because it allows us to understand how sustainable our labs are. And it's, we recently enhanced it significantly a couple years ago, so it's a whole new user interface. It's very powerful. It had an original benchmarking tool, but this is a much more usable tool, very user-friendly. It's been worked on by not only ourselves, but also, again, one of the DOE labs. This is the Lawrence Berkeley National Laboratories, and also, again, sponsored by the Federal Energy Management Program. It's free to use. You can use it yourself. You can benchmark your lab building. Basically, you put in your energy consumption, like your monthly energy bill consumption for like utilities. Put it into it, and then you can put in some other information about your laboratory, and then you can see where you stand versus other sort of peer type labs. One of the things that's important is that it was more of a US-based tool because it was sponsored by the US government, but we also got some other funding. Siemens was one of our sponsors for this, and we've now added metric units, very important, and we've also added, we're in the process now as we speak of adding climate zones around the world, so Israel would be covered. We're also adding all the country codes, the greenhouse gas factors for different countries. So within a couple months, you'll be able to put in your data as well and see where you stand. So, and this sort of shows a little bit of what it looks like. Basically, we can plot different parameters against each other, and then you can see where you stand, your lab versus other labs. So it's a very powerful tool. We have over 900 labs in the database, so it's almost probably 5% of the U.S. Total, over 125 million square feet, so maybe 11 million square meters. There's other tools. Part of it, there's what we call actionable insights that look at your building and sort of give you suggestions of what you can do to make it more sustainable. The data can be entered in through different approaches. So in the U.S., we have what we call Energy Star, which is a system by the government that allows you to put in your data and benchmark the data. Unfortunately, it doesn't work with labs, but the data can be pulled from Energy Star into our system, and then you can benchmark. And then there's operational practices. You can sort of benchmark your practices against others. That's another tool of the system. So it's a very powerful but easy to use tool. But it does have some limitations, and one of the limitations is that it can't actually give you a score. You can sort of see roughly where you stand, but it's more what I would call a qualitative adjustment or measurement, not a quantitative one. And many times people want to be able to say, well, how do I really compare against those labs more on a quantitative basis? And how do because I can look at a lab, and you can look at a lab, and we might look at ourselves a little bit differently. The question is, how do I get a single score? Sort of like LEED. How do I LEED Platinum or this, how do I get a more of a definitive quantitative measurement? So that's something that I've looked at it as being important. As I said, there's no means of doing that today for laboratories. And when you look at the sustainable systems like LEED, like Green Globes, if you're familiar with that one, or the International Living Future Institute has a zero carbon rating system, and Energy Star, this group in the US government, has a way to rate labs. But none of them rate laboratories. I mean, the Energy Star looks at buildings, I'm sorry, not laboratories. So the question is, how do I actually look at labs? And unfortunately, there's not really a good tool. I mean, you can obviously certify your laboratory under LEED, but it's not really certifying the energy performance. I mean, it's one of the many measures, but I've seen many LEED Platinum buildings that are energy hogs. They use a lot of energy. So it's not really a good representation of the energy efficiency of that laboratory. It may be very sustainable in other ways, but not necessarily in energy or carbon emissions. So that's what we wanted is I felt there was really a need in the marketplace for this. And so based on that, we've looked at this, and people have said to me, well, why hasn't LEED done this? Well, actually, LEED tried to do this with our help. I2SL worked with LEED to try to develop a LEED for Labs program back around 2012, and there was a lot of effort put into this. But at one point, the LEED organization, the USGBC, the management looked at this and said, this is just too complicated. It's not a big enough market. and it's just not worth the effort, and they shut down the program. So very tragic in my mind. But it was because labs are complex. I mean, we know that. They're very different. You have many different types of laboratories, whether it's chemistry or vivarium or biology, physics. They're all very different. They have different energy consumptions. A teaching lab is different than a research lab. How many hoods they have is a big impact. Is it 100% labs, or is it 30% labs, or 20% labs? That has a huge impact on the energy consumption. So the problem is it's not a simple solution. But fortunately, we've done a lot of that in the lab benchmarking tool. We just have not done the extra work to do the scoring. So that's what we want to do now, is build a score that uses techniques that's, basically what we would call a decarbonization scorecard. So the idea is to create a system like what the U.S. uses for Energy Star, which is a building system again. It doesn't cover labs, but our approach will cover labs. And what we'll score is operational energy, or energy use. We'll score carbon emissions, operational carbon emissions. And our goal in the future is to cover embodied carbon, sort of like the concrete and steel parts of a building as well. So now you'll be able to, whether your lab is a vivarium or physics or chemistry lab, you'll be able to get a score that allows you to compare the relative energy efficiency of your building versus like buildings in a quantitative means. It'll cover design, so you can say, I want to have a 80 percentile lab, it's a platinum lab, and we can then work backwards and say, what does that mean from an energy perspective for your building, for your type of laboratory? As well as you can create a new lab, energy use, or an operational energy use of an existing building. And then on top of that, we'll then certify it too. We'll have a third-party certification program, so we'll be able to have a third party, it could be here in Israel, some groups here, which would then certify the building and say, yes, that your meters are working correctly, the building is safe, so we want to ensure that the building is operated in a healthy manner, not just shutting off your air intakes or randomly reducing air changes, that you're operating the lab safely. But with that in mind, yes, the building is running in an efficient, low-carbon means. And lastly, be able to celebrate and recognize buildings for their achievements like you have for a LEED building. So again, how do we do this? It gets into the math. It's basically uses something called linear regression analysis. It allows us to basically look at their relationships between the different buildings, and we have a large enough database that we now can do that. So this is something we're going to work with Lawrence Berkeley National Labs. The DOE has said that they would help us with this, so we'll be working with them on it. Again, there may be some target data collection. You may do some modeling, but again, we've got this. This is something that's doable. We'll be able to do this. So what I've been doing is market research, understanding some of the market needs and what we want to do for this. And we're planning to have a final decision to go forward with this program, we think in July, so I'm pretty confident we're going to go forward with this. And again, I'd love to get into your thoughts on this concept, and if there's input here from Israel in terms of how you're using your laboratories and what you're looking for that, we'd be very interested in that as well. So with that, I just, again, to summarize, again, designing, new labs should be done on a net zero basis. It's not impossible. It's easy to do. Technology's out there. It's not Star Wars. This is common approaches. Even if you don't want to spend and buy a big photovoltaic array, you can use these power purchase agreements to be able to basically buy new solar capacity, which will then be effectively balanced out against what your building is using. And we need to do this quickly. Again, it's not the future. The future is now. We have to start doing these movements to make these reductions in our carbon emissions, or we as a species will cease to exist. So it's for our children, for our grandchildren, we need to do this now. And again, as I said, we can help. I2SL is here with its resources, and again, we'd love to create an Israeli chapter that would be basically helping in this effort and a way to spread knowledge to you and others. So thank you very much. Appreciate that. I don't know if there's any questions or
any questions? Sheilot?
In many laboratories, the biological and chemical solvents, vapors, are emitted from the fuels.
Right.
Currently, do you do something about it, or any thoughts what to do with it?
So you say they're emitted from you're saying that some of the labs, the humans are leaking, basically? Is that what?
Through the exhaust system. They're not scavenger. or any system to absorb laboratory fluid solvents, vapors, or at least currently. So in total, when you have so many fluids, many vapors go out to that.
Right. So the question is, you're asking whether we should be scrubbing the fume exhaust? Is that what you're suggesting? Yeah. I mean, we haven't seen that much done in the U.S. I mean, usually the prevailing opinion is that this is going to go out the top, and as long as we do studies which can be done, wind tunnel studies, to make sure that the fumes will not be readjusted back into the building, at least not to to a very minor extent. So definitely those studies are done where they basically look at the exhaust stack locations, they look at how much is emitted, and they ensure that that will not come back into the building. But to your point, I mean, usually in labs the assumption is, well, it's going to go out the top, it's going to get diluted, it's not going to go back into the building, it's not going to go into other buildings, and that's okay.
What about decarbonization? It's also part of that.
Yeah, I guess, well, that's a good point. I guess, but most of, I mean, that gets to what type of materials you're using. So that gets back to the chemistry of what people should be doing, because you're right. I mean, obviously there's certain materials which are horrible. I mean, for testing hoods, as an example, I mean, this is not the research, but when people test hoods, the common approach was to use a gas called sulfur hexafluoride, SF6. Turns out SF6 is a horrific gas. It's green, it's warming, global warming capacity is like 35,000 times of carbon dioxide. I mean, so someone testing a hood is equivalent to running the hood for like 3 months or something. It's crazy. So that gas has been banned, and now we're looking at isopropyl alcohol or other chemicals that are safer from that greenhouse gas emissions point. But so I think to your point, I mean, that's another aspect. It's not the building. That gets to the other side of what I call below the ceiling. So now, because we have to look at both. I mean, I agree that we want to make the building sustainable, but then we have to look at what the scientists are doing as well. And as I said, that's our, I wouldn't call them a partner, but sort of a we work with them quite closely. It's this group called My Green Labs. And that group basically focuses on the scientists and their scientific behavior. And they actually have their own certification program called the My Green Labs certification, which it looks at these issues. I think you had out there studying shutting the sash and doing different things that it's behavioral-based issues around things like chemistry and waste minimization, and those are very important as well. So we have to look at both. We have to look at the building as a structure